Turns out that these enantiomers and chiral compounds can interact with plane polarized light in a very interesting way. So before we get into that, though, we need to review what plane polarized light even is. So light is made of waves of electricity and magnetism, right? Electromagnetic waves. Now, in a regular beam of light, the electric wave of an individual photon can oscillate in any direction, 360 degrees. Right, so this gives a beam of light composed of many photons the appearance of simultaneously oscillating in all possible directions and all possible orientations. But what we can use is something called a polarizing filter. It can be used to align photons that are not oscillating in a specific planar orientation into just a specific direction. So effectively, photons that are oscillating at 90 degrees to that filter are effectively eliminated. So let's take a look at this little picture down here below and see if we can make some sense of what's going on. All right, so here's our light. It's moving in all possible orientations, right? Just showing a little sample of that, but in every orientation. All right, now the light that is 90 degrees to kind of the lines, the polarizing filter in this, are going to get filtered 100%. Now this light that's standing perfectly up and down follows the pathway of the polarized filter, kind of slits, and it passes through at 100%. Now the light that's between here and between here is going to get redirected and become in plane essentially with the direction of the filter. Some of that light intensity or the brightness of it will also be lost here. And in the end, what we have is light that is polarized and aligned in one direction. So down here below, here you have two polarized filters with their axis parallel, so light can go through. It's a little darker in the middle because there's just two filters on top of each other. If you take one of the filters and rotate it, like down here 90 degrees, then you're going to get that light being canceled out 100%. So in other words, light would get adjusted up and down, but the next filter has its filter oriented this direction rather than this direction. So it would eliminate a light at 100% right in the middle. If you stick a third filter in the middle and give it a little twist, then that redirects some of that light, right? Remember, it's only 90 degrees that gets eliminated entirely. So here, kind of in the middle, we end up getting some light coming through, right, where this light is still just an overlap of 1 and 2 on top of each other. All right, now let's take a look at this optical rotation. So it turns out that chiral molecules rotate plane polarized light. And what we have to do in order to see this is we set up an experiment that looks something like this. So we have a source of light. This is going to be for us like a sodium lamp. And then next we're going to have a filter. So this is just a monochrome filter, just so that we have only kind of one color coming through. And then that light's coming through now in just one color. It's moving all directions still, if you can see by the arrows here. And then here we have a filter. This is our polarizing filter here. Right? And that's going to align our light waves just in one orientation here. So we're going up and down. And now what we have over here is our sample cell. So you have whatever compound you're looking at in there. And notice as the light passes through, it's getting bent in one orientation. And down here at the other end, you have your eye, you're looking down, and you have something that you can kind of adjust around this filter essentially to try to see the light that comes through. And that light either is going to give you this minus rotation or this positive rotation here. So dextrorotatory is called a positive number, or it's clockwise, and levorotatory is negative. Counterclockwise are sometimes called anti-clockwise. And that's going to be your observed rotation. Now, the specific rotation down here is taking this a little step further. So we're going to take our observed rotation and we divide it by our concentration times the path length. Right? So it depends on the path length of our cell here. Okay, And what we're going to get is a number. If you have a mixture of enantiomers, enantiomer number 1 is going to give you a positive number, and then the other enantiomer would give you a negative number. There is no, this is important, there is no relationship between R and S and plus and minus. So you can have an R that's plus in one situation and an R that's a minus in another situation. There's not a relationship between the two. Now, a couple of important points just to mention here. When a sample has a mixture of the two enantiomers, the observed rotation will be less than the maximum possible rotation. So if it's negative 45 degrees and then a positive 45 degrees, then if a mixture is present of those enantiomers, you're going to be somewhere in the middle. Now, what happens if you have exactly 50-50? So 50% of the time you're getting a negative 45, and then the other you're getting a positive 45. So they just cancel each other out, and then you end up getting an observed rotation of 0. And that's called a racemic mixture. And we often indicate that by writing a plus and a minus in front of the name. It just means we have a racemic mixture. Now, as a result of reactions, and we're going to get into some really exciting reactions coming up here soon, but some of our reactions give us a racemic mixture because we have a 50-50 chance of the reaction occurring at one face of the molecule versus the other face of the molecule. So in this example down here below, hydrogen can add across this carbon-oxygen double bond, and when it does so, you get your H's up like this. And that gives you this R conformation. Now, if you come down here from the bottom, because you have a 50% chance of coming down here too, that puts the H down here in the bottom, and that gives you the S. And in this case, you end up getting about a perfect racemic mixture of enantiomers. So this would be a plus-minus situation as far as the naming of it, since you have about equal amounts of them. So how does this idea of stereoisomer affect our free radical halogenation? Well, we went through that chapter without really considering stereochemical consequences. Let's take a closer look at what's going on here. So let's look at this example. So let's add to this our bromine radical here. So the first step of this, and I want to go ahead and I'm just going to take off one of these H's here, so it doesn't really matter which one. Let's take that off, okay? So that's going to give us CH3 carbon, and now our H is going to be in plane, and a CH2 and another CH3 plus HBr, and that's going to be a radical. So let's talk about the structure of this just a little bit. So when we look at that radical, that alkyl radical there, we're going to have a carbon atom here, right? And what's sticking off of this is a methyl. So here I'm just going to write Me for that methyl. And then we're going to have an H coming off of this and an ethyl. So I'm going to put my ethyl here and put an H right there. Okay, and now when we put this on its side, we're going to have a p orbital here. Now that p orbital, if you remember, is going to have an electron hanging out up here. And remember, it also can have the electron in the lower lobe too, right? So in other words, we also get this. So that's what's going to react in the next step. In the next step, it's going to react with bromine. So if we have bromine coming in, bromine can come in this direction, right? Or it could come down this direction, right? So when it does that, we're going to get a mixture of products here. So let's take a look and see what we would get here. So let's take these two structures right here. And let's see what happens when they react in this next little step. So now as we react here with bromine, if we react on that top lobe, then bromine comes up here. We have our carbon, and then our methyl is going to get pushed down. Our ethyl gets pushed down, and our H comes back just like this. And then the same idea down here below. So as we approach from the bottom, then our bromo would come down, and then it would push our methyl up, our ethyl up, and our H back. Now the relationship between these two structures, these are enantiomers of each other. Now the way that we would often draw this out, by the way, is we would just look at the line structure. So we would go like this and say, okay, there's an H there. We would write it out like that. And then when we add to this bromine, I'm running out of space here, we would understand that you have a p lobe that's coming out towards us off of that carbon and a p lobe that's going back. Right, so in one case, what we're going to end up getting is the bromo coming from the front. And when it comes from the front, it'll be pointing out like this. Right, if the bromo group comes from the back, then it would be on a dash. Right, so this structure here, these two structures here are the same as the structures that we drew on the other side. And we don't typically draw them out like this other than showing specific things like stereochemistry. Now the last thing to mention here is that there are some physical properties that are kind of different from enantiomers and diastereomers. So real quickly, enantiomers have the same physical properties: melting point, boiling point, refractive index, density. One difference is that they rotate plane polarized light in different directions. Diastereomers have different physical properties. So plus minus 2,3-dibromo-succinic acid has a melting point of 158. Right? The meso form of that is 256. That's a big difference. The enantiomers we have to use chemical means to separate, and diastereomers, because their physical properties are different, it turns out we can use physical methods to separate. And enantiomers are going to have different interactions with other chiral molecules. Well, this is why spearmint oil and caraway seed oil smell different in your nasal receptors, because they're interacting with chiral molecules in your nose differently.